Now we see about the determination of resonant frequency of series and parallel RLC circuit. Already experiment 6A we have series circuit. Here 6B, experiment number 6B, we have parallel circuit 6B. Okay, so what is the aim? To design RLC parallel resonance circuit and obtain the resonant frequency. So based upon that aim, we have to design the apparatus. So this is the apparatus required table, that is resistor, capacitor, DIB, that is decayed induction box, then function generator, CRO, breadboard and connecting wires. So this is the circuit diagram. Okay, here parallelly connected. So this is the operation, that is inductance and capacitor, then resistor. So that's why we can say it is RLC circuits. Here inductance and the capacitor connected in the parallel. So here the resistor is available. Here CR, this is function generator, input we have to give. Then for the CRO, cathode ray oscilloscope, we can give the output. So this is the model graph. Right, now we see about the circuit. So before that, this is the DIB, decayed induction box. Okay, decayed induction. I have to put the range. So if you want to change, if you want the range for 100 microhenry, for the 800 microhenry means we have to change the knob, we can get it. But our circuit itself we have only for the 100 millihenry. So where it is available, see, this is the 100, this is the 1 millihenry, this is the 10 millihenry. Here we have the 100 millihenry. Finally we have the 1 henry, like that. So we have only for here in the circuit itself we have 100 millihenry. No, so I have to arrange it here. This is the 0. So here I have to change it only for the 1. So because it is the 100 millihenry, this way we have to arrange it. Okay, this knob denoted as a 1. So this 1 into 100, we have a 100 millihenry. So because your circuit we have the range 100 millihenry, L is equal to inductance. Okay, 100 millihenry. Here see that is a 0.1 microfarad. So this is the capacitor, it's a 0.1 microfarad, right? So the lengthy line we can say it's a positive, and the short line, needle we can see is the negative. That's a terminal, not the needle, there is a terminal, there is a positive and the negative. Then we have the, this is a 10 kilo ohm. So 10 kilo ohm, what is the range? Brown, black and orange. Okay, brown is a 1, black is a 0, then orange is the multiplier. No, so orange is a third color, so you have to multiply, so 10 power 3. So finally we get the range of the 10 kilo ohm. Okay, so this is the resistor. So here inductance, capacitor and the resistor. Now this is the function generator, right? That is, we have to give the input, that's the frequency ranges, all the process we can choose for the that is a function generator. This is a CRO, this is amplitude knob, this is the time period knob. We have the channel 1, channel 2, this is the probe. So in probe we have the positive and the negative. Here the positive probe, this is black, is called as the negative probe. Okay, so likewise for the function generator itself we have the positive and the negative probe. Okay, so these are all the connections, these are all the component whenever connecting the parallel circuit. Now we move on to the circuit connection. See, first of all I have to put, this is the induction, this is the positive and the negative. So plus and minus, no, that is the plus and minus. Okay, so I have to take this one. So parallelly we have to arrange it, inductance and capacitor. Okay, so I have to place it any one of the place in the breadboard. So here for the negative component, negative side I have to put the breadboard. So this is the first connection, right? Inductance box. Next I have to take the capacitor, because your circuit having parallel, no, so this connection is finished. We have to move for the capacitor side. So I have to put the positive one and the negative, right? So here for the, I have to put the parallel, right? So parallelly I have to insert at the capacitor, right? So this is the inductance, this is the capacitor. It is connected in the parallel form. Okay, now I move on to the third component, the resistor. So in between of the capacitor and the inductor, I have to place it the resistor. So this is the 10 kilo ohm. So this is the inductor negative, right? See, inductor negative and the capacitor negative. In between gap, I have to place the resistor. So this is the capacitor negative, this is the inductor negative. I have to place it here. Resistor another end is moved to the ground. See, right? Resistor another end is moved to the ground line. So I have to place it here, ground line. Okay, three components are connected. Now you have to take the input section, the function generator. Already I explained, no, positive and this is the crocodile probe. So here the red is the positive and the black is the negative. Okay, so here A4, here the in between of the inductance and the capacitor positive end, we have to connect the AFO positive. This is the AFO positive. See, red, I have to place it here. This is the inductor positive, this is the capacitor positive. I have to insert it here, right? Okay, then negative should be the negative probe. It should be the ground. Okay, it moved to the ground. So that's all about the A4. Then I have to go for the probe of the CRO. So I have to take in the CRO probe. So these are also positive and the negative. Okay, so what is the connection? See, so in between of the inductor, capacitor and the resistor, in between we have to connect the CRO positive. See the connection, right? Here we have to, so I have to insert the capacitor in one end. Okay, right? So in between of the inductor, capacitor and the resistor, I have placed it here, CRO, right? CRO positive, and then another one is I have to place it negative. Okay, so that's all. So this is the connection. So after that connection, we have to switch on the AFO and the CRO. So see some reading, no? Right? If you arrange for the minimum frequency range. Okay, minimum frequency range means we can get it the result. Okay, we have to change the function also. So if we get the result. Thank you, students. Students, now we see about RLC parallel circuit output. So here the concept is, if you're having the frequency level 280 Hertz means here the amplitude value 4.2. So if you raise the frequency level means it may be reduced, and again we can increase means we get the final value of model graph like that. Okay, so this is our parallel circuit model graph. Okay, having increased level, then decreased level, then it can be increased. So this method we have to get the reading. This is the correct concept of the parallel circuit. So based upon that, I have to take reading, see the reading level. So I have to adjust the frequency level. This is the hold button, how to stop the signal. Okay, so see 280 Hertz, here having 4.2 volt. I have to write it here 280, here 4.2 volt, but 4.2 we have to multiply with the CRO knob. Already I have explained in the series circuits. Okay, here the same procedure how to follow. Here 4.2, having 4.2 into 0.5. Okay, here we have to get 2.1. 4.2 into 0.5, we have to get 2.1. Right? So now I have to increase the level. I increased 500 Hertz. Okay, see the changes in the AFO. See the amplitude changed. Okay, here same level it will be maintained. So I have to bring to the 700. I have to increase the frequency level. Right, so nearby 700, here we have to get 4.4. Okay, if you arrange the frequency level 700 means we have to get 4.4 into, we have to multiply it with the CRO knob 0.5. okay, 4.4 into 0.4 we can get 2.2 like that. Okay, so now I have to increase the level 1000 hertz. okay, 1000, then we get the result. One, two, three, 4.2. Here also 1000 hertz itself we get the 4.2 into 0.5. So 4.2 into 0.5 we can get it 2.1. okay, I have to increase 1500. See the sudden changes of the amplitude. I have to put 1500 hertz. See, amplitude reduced. okay, here the Y position I have hold it. See the reading level 1 2 3 3.2. so 3.2 into 0.5. okay, so 3.2 into 0.5 1.6. okay, now I have to increase 1500. Already we have the value 1500. Now I increased 1600. okay, see exactly I have to put 1600. then amplitude reduced. See 1, we are having Y position 1.4, 1600 hertz 1.4 into 0.5. so we have to multiply 1.4 into 0.5, that is 0.7. okay, again I increased 1700. see the changes, sudden changes. amplitude level increased. I have to put now 1700 hertz. so here the reading, so I hold it, right, 1 2 2.246. here 1 2, here 0.2 0.4 0.6 0.8 1 1.2 1.4 1.6 1.82 2.2 2.4. so 2.4 into 0.5. okay, here 2.4 into 0.5 1.2. okay, again I increased. I have to put 1800, right, I have to put, right, so hold the signal 1800 hertz. see the level 1 2 3 3.6. so 3.6 into 0.5, 3.6 into 0.5 we can get it 1.8. again I increase. Two 2000 hertz. I have to put 2000 hertz. I hold it. Now we can get the 1 2 3 4. So exactly 4. 4 into 0.5, right? 4 into 0.5 we can get 2.0. okay, so this is the 2000 hertz, right? If you raise 2100, 2200, so see the signal. that much of value raised, that is the maintained as a level 4. So 2200 hertz. So 4.0 into 0.5, we are having 4.0 into 0.5. So what is finally we have to conclude, if you increase and decrease the frequency based upon the amplitude value will be changed. So for the gain calculation, so 20 log 10, here V0 is a 2.1, this 2.1, okay, 2.1 divided by Vn, that is 2 volt. Okay, so we have a calculation. Here's the first, we have to take the log, then we have to open the bracket. So V0 value is here, see, V0 value 2.1, no, so 2.1 divided by V in value 2, okay, then we get the result like that into 20, right, that is 0.4237. This is, so we have to write it here, 0.4237. Like that we have to calculate the second calculation. So 20 log, here V0 is a 2.2 divided by 2, okay, at a time log of 2.2 divided by 2 into 20, so we get 0.8278. so 0.8278. Likewise we have to calculate the reading. Then using similar graph sheet, you should draw the graph. Okay, the curve should be increased level, it will be reach the decreased peak level, then it will be increased. This is the final